In the study of linear algebra, algebraic equations dictate how geometric structures intersect and lock together in physical space. On this Cartesian coordinate plane, we have two distinct intersecting lines. We define these lines using their general form equations. Line 1 is a1x plus b1y plus c1 equals 0, and line 2 is a2x plus b2y plus c2 equals 0. The a and b coefficients are the specific values that determine the orientation of these lines. For this derivation, we are looking at non-vertical lines, meaning the y coefficients, b1 and b2, are not 0. Standard geometric analysis determines if these lines are parallel or perpendicular by first calculating their slopes. However, it is possible to derive direct geometric conditions using only the a and b coefficients, bypassing the need for intermediate slope calculations. Using these coefficients directly creates a more efficient verification process, allowing for rapid geometric classification without converting the entire equation. To find the connection, we start by isolating the slope within the equation of our first line. Our goal is to transform this general form into the slope-intercept form, y equals mx plus c. We move the x term and the constant to the right side of the equal sign. Then we divide the entire equation by the coefficient b1. This is possible because our initial requirement is that b1 is not 0. We now identify the slope of the first line, m1, as negative a1 over b1. Applying the same steps to the second line gives its slope, m2, negative a2 over b2. These two expressions serve as the link between the coefficients and the geometry of the lines. We now use these slopes to test our conditions. For two non-vertical lines to be parallel, their slopes must be equal. Substituting our slope expressions, we get negative a1 over b1 equals negative a2 over b2. We simplify by canceling the negative signs. To clear the fractions, we use cross multiplication. By multiplying both sides by the product b1, b2, we remove the denominators. This yields our final condition for parallel lines. a1, b2 must equal a2, b1. This cross-multiplication provides a direct test for parallel lines, using only the coefficients, removing the need to work with fractions. Next, we derive the condition for perpendicular lines. When two lines are perpendicular, the product of their slopes is negative 1. Again, we substitute our slope expressions into the equation. Multiplying the two terms causes the negative signs to cancel out. The result is the product of the a coefficients over the product of the b coefficients, which equals negative 1. We clear the fraction by multiplying both sides by b1, b2. This gives us a1, a2 equals negative b1, b2. Finally, we move the term from the right side back to the left, setting the sum to 0. This establishes the perpendicular condition, a1, a2 plus b1, b2 equals 0. This relationship allows us to confirm if two lines are orthogonal by checking if the sum of the products of their coefficients is exactly 0. These foundational algebraic rules give us a direct, immediate way to visualize complex spatial orientation in physical space. Both conditions are now defined entirely by the coefficients of the general form. When a1, b2 equals a2, b1, the lines are parallel. When the sum a1, a2 plus b1, b2 is 0, they are perpendicular. This derivation provides a definitive way to characterize the geometry of a line directly from its equation. By using these rules, we can determine the relationship between two lines without the extra step of solving for y. Learning to apply these conditions allows you to select the most efficient algebraic path for any geometric problem.